So hello everyone, welcome to this NPTEL course on cycloaddition reaction. So this is a short course where you have 20 lectures, and in this course we will talk about three important cycloaddition reactions, namely 4+2, which is also called Diels-Alder reaction. Then we will talk about 3+2, which is also called 1,3 dipolar cycloaddition reaction. Then we will go to 2+2 cycloaddition reaction. What we will do, more than 50% of the lectures will be on 4+2 cycloaddition reaction. Before we actually go into discussing about cycloaddition reaction, I will give a brief overview about how organic reactions are classified. Let us start with that. Organic reactions are classified in many ways, but what we do, we will classify in such a way that has some similarity with music. Okay, and after this discussion you will know how organic reactions have close similarity with music. So this is how you do organic reaction, and this is how you play music. And as I said, organic reactions can be classified in many ways, and one of the ways is it is classified into 7 different types. First one is addition reaction. As you know, there are many types of addition reaction: nucleophilic, electrophilic, free radical. So then opposite to addition is elimination reaction. So it can be E1, E2, E1CB and syn elimination and so on. Then we have substitution reaction. It can be aromatic, it can be aliphatic, again it can be further divided into electrophilic substitution and nucleophilic substitution. You have oxidation reaction. Opposite to oxidation is reduction reaction. Then comes one which we are going to discuss in details, that is pericyclic reaction, and the last one is rearrangement reaction. So now if you look at these 7 reactions and why we are comparing with music, as we all know, music has 7 swaras. If somebody sings a song, and if you know all the 7 swaras, it should be easily possible for you to identify which swara that song belongs to. Likewise, now once you know all organic reactions, then it is possible for you to identify a particular reaction, whether it is one of this reaction or more than one of this reaction. So that's how you can see some similarity between organic reaction and music. And now let us go to the topic of our discussion, that is pericyclic reaction, under which the cycloaddition reaction will come. Cycloaddition reaction is a reaction which comes under pericyclic reaction. So what is pericyclic reaction? The name itself suggests peri and cyclic. That means it involves peripheral electrons and the reaction goes through a cyclic transition state. Okay? And the whole reaction also goes through a concerted process and without intermediates. When we talk about concerted process, which means the breaking and making of bonds happen simultaneously, but sometimes it need not be synchronous. So this pericyclic reaction can be classified further into 5 types. 1, the subject of the topic today, that is the cycloaddition reaction. 2, we have sigmatropic rearrangement. I am sure many of you would have studied 3,3 sigmatropic rearrangement like Claisen, Cope, etc. Then we have chelotropic reaction, which is mostly elimination reaction. Then group transfer reaction, where groups are transferred from one atom to another. And finally electrocyclic reactions. So what we are going to do is we are going to focus only on cycloaddition, and the next slide onwards we will discuss more about cycloaddition reaction. Again, when we talk about cycloaddition, the name itself, if you look at cycloaddition, that means two substrates undergo addition reaction to form a cycle, or a new ring is formed in this reaction. Okay, cycloaddition. Okay, a ring is formed. It can be two different substrates react under concerted process to form a ring. And normally when we look at cycloaddition reaction, you also see these cycloaddition reactions are written as A plus B in square bracket. So what are these A and B? The A and B normally refers to atoms. A and B represents the number of atoms having pi electrons. Okay, it is, for example, you have A is 4, then A should have 4 atoms having pi electrons, and if B is 2, that means 2 atoms should have pi electrons. So that is how this A and B designation is given. And how do you further classify cycloaddition reactions? So already we classified organic reactions, then organic reactions, under that pericyclic reaction, now under that cycloaddition reaction. Now how cycloaddition reactions can be further classified? So there are quite a few types of cycloaddition reaction, but for this course we will restrict to only 3 types. One is 4+2 cycloaddition reaction. That means this particular reaction involves 4 atoms having pi electrons reacting with 2 more atoms having pi electrons. So this is also called Diels-Alder reaction. So then the second one is 1,3 dipolar cycloaddition reaction. Here is also called 3+2 cycloaddition reaction, which means it has 3 atoms having 4 pi electrons and 2 atoms having 2 pi electrons. Then the third one is 2+2 cycloaddition. That means here the 2 components are having 2 pi electrons. So now let us start with Diels-Alder reaction. The Diels-Alder reaction was reported by Otto Diels and his student Kurt Alder in 1928. For this major discovery, they received the Nobel Prize in 1950. So this is Otto Diels and this is Kurt Alder. And what is important was, it was though looking like funny now, when they reported this reaction, they mentioned in their paper this last paragraph that they explicitly reserve the application of this reaction and nobody should use this reaction. So remember, such a good reaction, if no one used, then this reaction will be applied only by his research group, and obviously as a result not many good publications would have come. But what happened? People just ignored this last line and they started using the reaction left and right in the application of synthesis of several natural products. In fact, that was the reason why they got Nobel Prize, because whenever a new reaction is developed and if it finds wide application, then the chances of getting recognition is very high. That's how they got Nobel Prize. And what is Diels-Alder reaction? So the Diels-Alder reaction, as I said, it's a 4+2 cycloaddition. That means 4 atoms having pi electrons and 2 atoms having pi electron. So the 4 atoms, that means 2 double bonds are attached in the 4 carbon atoms. So it should be a conjugated diene. It's very important. the diene should be conjugated. Unconjugated diene cannot undergo Diels-Alder reaction. Then the Dienophile. The Dienophile is nothing but 2 atoms having pi electrons. So when you have 4 pi electrons and then 2 pi electrons, when they react under this, what we call it as Diels-Alder reaction, 4 plus 2, that means you should get a 6-membered ring, that is cyclohexene ring. And this is one of the best methods in organic chemistry to make a 6-membered ring. So for example, you take a butadiene and then treat with ethylene. So this should give cyclohexene. So if you look at this transformation, so what you get is in the starting materials, that is you start with diene and dienophile, there are 3 pi bonds, okay, but in the product you have only 1 double bond. That means the change is -2, whereas the sigma bond, if you see, you are gaining 2 additional sigma bonds. So the change is +2 as far as sigma bond is concerned. Okay. What are the various types of Diels-Alder reaction? So we started from organic reaction, then pericyclic reaction, then cycloaddition, and in the cycloaddition now we are talking about Diels-Alder reaction. And what are the various types of Diels-Alder reaction? So normally the Diels-Alder reaction is broadly classified into 2 types. One is intermolecular reaction, that means the diene and dienophile are 2 different species. The second one is intramolecular 4+2 cycloaddition. That means the diene and the dienophile are part of the same substrate, or in other words, the dienophile is connected to the diene. So these are the 2 major types of Diels-Alder reaction. Let us start with intermolecular Diels-Alder reaction now. So again, this intermolecular Diels-Alder reaction can be further classified into 3 types. One is normal 4+2 cycloaddition reaction. So what is this normal 4+2 cycloaddition reaction? That means the diene which is used for this Diels-Alder reaction should be electron rich in nature, while the dienophile which is used should be electron poor. Or in other words, diene should have electron donating substituents attached, whereas electron withdrawing group should be attached to the dienophile. The second type is when we talk about normal, the second type should be exactly opposite, that means abnormal. If we call this as normal electron demand reaction, this one, normal electron demand reaction, the second one which is abnormal 4+2 is called inverse electron demand 4+2 cycloaddition reaction. What does it mean? In the case of normal 4+2 cycloaddition, the diene should be electron rich and the dienophile should be electron poor. And the opposite of that is here the diene should be electron poor. That means electron withdrawing groups should be attached to the diene and electron donating groups should be attached to the dienophile. So now if you look at these 2 types of Diels-Alder reaction, we are talking about all the atoms are carbon, whether it is diene or dienophile, both the substrates have only carbon atoms which form the part of the 6-membered ring. Why? Why only carbon atom? You can also have heteroatom. So the third type is hetero 4+2 cycloaddition reaction. Again, when you talk about hetero 4+2 cycloaddition reaction, there are 2 possibilities. That is, the heteroatom can be part of the diene or the heteroatom can be part of the Dienophile. So these two possibilities are there under the hetero 4+2 cycloaddition reaction. So now when we talk about further, that is, you need a diene, you need a dienophile to undergo intermolecular Diels-Alder reaction. Now let us see what are the criteria for diene to undergo Diels-Alder reaction, or what are the requirements of diene to undergo Diels-Alder reaction. First of all, the diene should be either open chain compound or cyclic. Then, as I said, for a normal Diels-Alder reaction, for a normal 4+2 cycloaddition reaction to occur, the diene should be electron rich, or in other words, the diene should have electron donating substituents. Then the most important requirement is, when you talk about open chain or cyclic diene, the diene in principle can exist in two conformations. One is called S-cis, the other is called S-trans. Now when you look at these two conformations, you can immediately guess the S-trans conformation cannot undergo 4+2 cycloaddition, whereas the S-cis can undergo 4+2 cycloaddition reaction. Here what is S? S is nothing but this single bond. So if you look at the S-cis conformation, the two double bonds are cis with respect to the single bond, whereas here these two double bonds are trans with respect to the single bond. So that's why it's called S-trans. Now if it is open chain diene, then this CC bond can rotate. The free rotation is possible in the case of open chain diene. So it does not matter when you have open chain diene, whether it is S-cis or S-trans, the S-trans can undergo CC bond rotation to come to S-cis, and this S-cis will undergo the Diels-Alder reaction. However, if it is cyclic one, then it should be only in S-cis conformation. So here I have given 4 examples. As you can see here, all these cases, the single bond is having the two double bonds cis to each other. Okay, so only this S-cis conformation will undergo Diels-Alder reaction. Whereas if you look at these 3 dienes, now you can clearly see these two double bonds are trans with respect to your single bond. S-trans. Same thing, you see this is single bond, but both double bonds are trans to each other. Likewise, you can see you have single bond, both double bonds are trans to each other. But unlike open chain diene, here this CC bond rotation is not possible. When the CC bond rotation is not possible, the S-trans cannot come to S-cis. Then obviously these dienes cannot undergo Diels-Alder reaction. These 3 cannot undergo, whereas these 4 can undergo Diels-Alder reaction. Okay. Now I will just give few examples of how these dienes are prepared. So there are many ways one can prepare dienes. I will give only few examples through known reactions. See, for example, you can take any ketone. For simplicity, I started with acetone. Now you add a vinyl-Grignard reaction, it's a nucleophilic addition to form a tertiary allylic alcohol. Now this upon dehydration gives a diene. This is nothing but isoprene. Okay. So isoprene is commercially available, but one can also make like this diene through addition of vinyl grignard followed by dehydration. One can also use a base and then quench with TMS chloride of an alpha beta unsaturated ketone. So when you have an alpha beta unsaturated ketone, one can generate anion with a base, because this hydrogen is acidic, so you can deprotonate, and then this after deprotonation it can form enolate. That enolate can be quenched with TMS chloride. Now you can see this is a very good diene. One more way, one can use Shapiro reaction to form the diene. For example, if you take any cyclohexenones and treat with tosyl hydrazine, you will get the corresponding tosyl hydrazone. Now, if you treat this tosyl hydrazone with methyl lithium or LDA, it can undergo elimination to give you the corresponding diene. So these dienes can be further used in the Diels-Alder reaction. And the fourth possibility is, I don't know how many of you have studied, is called ring closing enine metathesis. That means the starting material should have an alkene, you can see an alkene and alkyne. This, upon treatment with ruthenium catalyst developed by Grubbs and others, this can undergo a series of 2+2 followed by retro 2+2 give such dienes. These dienes can be easily used in 4+2 Diels-Alder reaction. Okay. Likewise, what are the requirements of dienophile to be used in Diels-Alder reaction? Like dienes, dienophiles also can be open chain or cyclic compound, but for a normal 4+2 cycloaddition to take place, the dienophile should be electron deficient, or in other words, electron withdrawing groups should be attached to the double bond. See, for example, you can see all these have double bond. Okay, so these are dienophile, but what is important is, for the normal Diels-Alder reaction to happen, you have electron withdrawing groups attached to the double bond. So these four will act as a very good dienophile in 4+2 cycloaddition reaction. Likewise, now you have a nitro group, sulfoxide, sulfone, and in this case you have ester at both the carbons. So they all can act as a very good dienophile in normal 4+2 cycloaddition reaction. Okay. And if you look at this case, here you have anhydride and this double bond can act as dienophile. You have cycloalkenones, you have a ketone as electron withdrawing group. This is a lactone, can act as an electron withdrawing group. So this is a benzoquinone or substituted benzoquinone. You have two ketones which can be electron withdrawing. So how these dienophiles are prepared? Some of them are commercially available and many can be easily made. Say for example, if you use Henry reaction, nitromethanes and formaldehyde or any aldehyde, treatment with base or even direct treatment with acid, one can make nitroalkene or substituted nitroalkene. Okay. So this way it is very easy to prepare range of nitroalkene which could be used in cycloaddition reaction. And then if you have hydroquinone, 1,4-dihydroxy benzene or substituted ones, one can easily oxidize to get the corresponding benzoquinone or substituted benzoquinone. Then one can also introduce double bond next to ketone. See, for example, if you have cyclohexanone, one can introduce double bond next to the ketone. So there are two possibilities, or there are many possibilities. At least one is you can treat with LDA and phenylselenyl chloride. So it forms the corresponding the phenylserine compound. Now if you treat with MCBBA or any paracids, it can undergo oxidation of selenium to form the serine oxide, and that can undergo elimination of phenylserinic acid to form the double bond or to introduce the double bond. So now this can act as a good dienophile. Now the double bond is inside the ring. You can also introduce a double bond outside the ring. See, for example, in this case, you take any cycloalkanone and treat with formaldehyde and a secondary amine in the presence of acid. It's a well-known reaction called Mannish reaction. So you can easily introduce an exocyclic double bond. This exocyclic double bond now you can see can act as a dienophile, and it has electron withdrawing carbonyl group. And there are many commercially available dienophiles. For example, acrylonitrile, well known, and polyacrylonitrile, this is a starting material. You can hydrolyze, you can do a partial hydrolyze to get corresponding acrylamide, or you can hydrolyze to carboxylic acid and esterify, you can get the alpha beta ancel ester. And you also, if you have this compound, this is called acrolein, and this is also commercially available. So this is called methyl vinyl ketone, MVK. So this is also commercially available, and all this can be used as dienophile in 4+2 Diels-Alder reaction. So now let us see some simple example where your diene is symmetrical and same way dienophile is symmetrical. So look at butadiene. So it's a symmetrical compound, and dimethyl acetylene dicarboxylate is also a symmetrical compound. Now mix these two and heat it. As you know, all cycloaddition reaction do not need any external reagents. Either by heating or shining light, one can do this cycloaddition reaction. When we talk about 4+2 cycloaddition reaction, so if you heat it, it will give this cyclohexadiene. So normally if it is only the double bond, you will get cyclohexene. Since you are using a triple bond as dienophile, you get additional double bond. Now if you look at this diene, you can recall Birch reduction. So if you have to get a diene, normally people use Birch reduction. For example, if you take anisole and then do Birch reduction, so you get the corresponding diene. So you can also use electron withdrawing group. See, for example, if you take benzoic acid and then do a Birch reduction, you get the corresponding diene. So that is one way to get diene. Now you can also start with acyclic diene and acyclic dienophile to get cyclohexadiene, substituted cyclohexadiene. So instead of dimethyl acetylene dicarboxylate, one can also use maleic anhydride. So if you use maleic anhydride, you can get a bicyclic compound. Okay. Instead of maleic anhydride, if you use dimethyl fumarate, that can give cyclohexene with the two substituents which are coming from dienophile. And what is more important is, if you look at the stereochemistry of two esters, in the dienophile they are trans to each other, and the same thing you observe in the product. Or in other words, the stereochemistry of the dienophile is completely retained in the product. Okay. Now some more examples before we go to stereochemistry and regiochemistry of 4+2 cycloaddition reaction. You take the diene, for example, again we take butadiene and very strong dienophile. The earlier case we saw dimethyl dicarboxylate, dimethyl acetylene dicarboxylate. Here the two esters are attached at both the carbons, but here you can see the two esters are attached to one carbon. So it makes it more electron withdrawing. If it is more electron withdrawing, the chances of Diels-Alder reaction undergoing at lower temperature is very high. So, as you can see here, it can be done at room temperature to form this substituted cyclohexene. Now, acrolein is only one electron withdrawing group, that is aldehyde. So, obviously you have to heat it. So, when you heat it, you get this substituted cyclohexene. But remember, in this example, you are creating a new chiral center. Okay? Let us discuss this later when we talk about stereochemical outcome of Diels-Alder reaction. Likewise, you take cyclopentadiene and then treat with acrolein, and you get again more chiral centers. Okay? In the next few classes, we will talk in details about what about the stereochemical outcome of cycloaddition reaction and what are the regiochemical outcome of cycloaddition reaction if you have substituents in diene as well as dienophile. When you have substituents in diene as well as dienophile, then the concept of regiochemistry also should be discussed to see what is the final regiochemical outcome. Okay? So, some more examples. For example, if you take cyclohexenone, this also can undergo Diels-Alder reaction, and then now you get a bicyclic compound. Okay? And this case, as I said, when you have substituent in the diene and substituent in the dienophile, then in principle there are two possibilities. One, it can be 1,4 the substituent which is present in the dienophile and which substituent which is present in the diene. It can be 1,4 related in the product, or it can be 1,3 related in the product. Please remember, here we should not use the word para or meta. You should avoid using para and meta. In some textbooks they use, but it is not correct. The reason is we use the term para, meta, ortho only for aromatic compounds. If you look at these two, they are not aromatic compounds, they are alicyclic compound. So, you have to use 1,4 and 1,3 in this case, and in the next example you can see here, in principle it can give two products, and one is 1,2 adduct, the other one is 1,3 adduct. In the next class we will discuss both stereochemical and regiochemical outcome of this 4+2 cycloaddition or Diels-Alder reaction in details. Okay, thank you.